Good morning, everyone. My name is Naomi Simumba, and I'm here to present my research on a spatially and semantically diverse road path generation using hierarchical clustering. So to begin with, road path generation aims to create a path which prioritizes specific criteria. Specifically, when we are applying it in automated driving testing, we're trying to generate a series of points noted as points of interest, which will highlight different types of intersections which should be navigated successfully. The goal in this case is therefore to generate a path that is both semantically and spatially diverse for the automated driving vehicle to navigate. In this case, the types of input data that we might use would be spatial data, which would specifically be the locations, as well as semantic data, which is the type of points and their features. So the data inputs in this case are mixed. So we'll have a combination of text, categorical, and numerical values. So the goal that we must ask ourselves is, using this type of spatial and semantic data, how can we create a series of points or generate a path for the automated driving vehicle to travel that will be both spatially and semantically diverse? So next, I will briefly go over the types of data sources that we have available. We specifically move forward with using OpenStreetMap data, which is available from openstreetmap.com.org. OpenStreetMap data has a combination of location data, which are maybe nodes or ways as a series of nodes or points, as well as text data, which is in the form of tags. The tags have both a key as well as a tag value, which will have different types of tags. So for instance, a tag may denote the ID of the element or may denote the type of the element, such as the highway or residential area. Using OpenStreetMap data, for instance, in San Fernando Valley in Los Angeles, we would be extracting data that would be extracting roads that have, for instance, the tag network type drive service. So in this case, we'd be extracting roads that have the tag network type, as well as the key value drive service with coordinates given below. Looking more closely at the data within this region, we see that we are able to extract over 17,000 ways, which are our roads, as well as over 7,500 intersections, which you can see in this as our road network for experimental data. Now, considering the related work that exists in this space, we begin by considering the research titled Semantically Diverse Path Search by Teng and colleagues. In this case, the authors use the diversity aggregated R-tree method to select points of interest, such as museums, statues, etc., that tourists might be interested in. So they selected the points which would be diverse within a given distance of the starting point, and then connected the points to a path. So the emphasis in this case was on selecting semantically diverse, was on selecting the most semantically diverse path. They also defined a non-negative diversity score, which measured the subset of the points of interest selected. Other related research in this space was titled Automated Generalization of Road Network Maps by Pescia and Creveld. In this case, they modeled the road as an embedded graph and used selection criteria as follows: avoiding roads that were too close together, avoiding long detours, as well as preserving the most important roads. So some of the strengths of this research were that it allowed the authors to maintain connectivity. It allowed them to maintain reachability, which means that points could be easily reached by the determined road network. It also avoided detours and maintained the important roads for transport. However, the output may have removed some roads which would be needed for automated driving vehicle testing due to their semantic diversity. So next, I will introduce you to the methods that we are using for the analysis. Our hierarchical clustering process is composed of two steps. The first is a graph clustering process, which uses an adjacency matrix to distinguish the points spatially. Next, we use spatial clustering. We use spatial clusters applied with mixed data clustering to distinguish the points semantically. So the goal of this process is to select intersections that have maximum diversity. So we select the nodes that are closest to the center of the clusters by using the Euclidean distance, and then connect these intersections using the shortest path. So the input would be all the intersections that are within a given area. After the process of semantic and graph clustering, we end up with a path that is connected by the shortest path, composed of intersections that are both semantically and spatially diverse. Next, I will introduce you to the clustering methods that we will be using and the concept of graphs. So the spectral clustering process is a process that allows us to produce normalized graph cuts. And this allows us to detect the densely connected clusters within the graph. So this is the process that we will be using to produce our spatial diversity. The process of spectral clustering uses something called the adjacency matrix, which is a square matrix that is used to represent a finite graph. And the elements of the matrix represent whether or not two nodes in the graph are actually connected. Next, I will introduce you to the concept of the mixed data clustering with the node tags. So after the spectral clustering process, which will allow us to achieve the spectral diversity, we then go into a mixed data clustering process that allows us to achieve semantic diversity. For this process, the input data are the node tags. So for instance, we might have different types of data. We might have categorical data in the form of the words describing what type of road it is. We might also have a numeric data, which is in terms of numbers that are describing, for instance, the number of streets attached to an intersection, the length of roads attached to the intersection, and so on and so forth. So this is why we term this mixed data clustering, based on the data describing the intersections. So basically, the overall flow of this analysis process is as follows. We begin with input data from OSM, which is road network data from the San Fernando Valley area in California. Next, we perform the spectral or graph clustering process, which will allow us to produce subgraphs, which are the densely connected areas of the road within the area. Next, within each subgraph, we use the features of the intersection from the node tags from OSM to produce semantically diverse clusters. From this process, we then move on to a selection process where within each subgraph and also within each mixed data cluster, we select intersections with the smallest Euclidean distance to the cluster center. So we repeat this process until we have the maximum number of intersections that are required for this experiment. And we connect the intersections by finding the minimum distance between them. Overall, the output will look as follows. When we're using the proposed approach, as you can see, the output is shown above. We have selected the intersection. We find we find paths between the intersections that minimize the distance. And finally, we connect them to form a generalized roadmap, which is the path for the automated driving vehicle to travel on. Using the random method, is the application is seen below. As you can see, we are able to achieve points that are more spread out using the proposed approach. So finally, comparing the diversity of the two methods, we use Shannon's entropy, which is also known as the Shannon's diversity index, which is calculated by the equation shown below. So in terms of semantic diversity, we realize that the semantic diversity of the mixed data clustering method is actually higher than the semantic diversity of the random method. But the semantic diversity of the graph clustering method is lower than that of the mixed data clustering. With the proposed approach, we're actually able to achieve semantic diversity that is higher than using either a random method, using mixed data clustering on its own, or just graph clustering. Next, comparing the methods in terms of the spectral diversity. So in comparing them in terms of the spectral diversity, we realize that we are once again able to achieve a spatial diversity, that is actually higher than when we use just the random method, when we use the mixed data clustering, or just the graph clustering. So overall, we can show that our method is able to achieve both a higher semantic diversity as well as a higher spatial diversity, which was our desired goal. Thank you so much for your time.